Okay, we're on exercise 11 of the NMSI packet for acids and bases, and this one deals with the pH of weak acids. So I'll read the question. The hypochlorite ion is a strong oxidizing agent often found in household bleaches and disinfectants. It is also the active ingredient that forms when swimming pool water is treated with chlorine. In addition to its oxidizing abilities, the hypochlorite ion has a relatively high affinity for protons. It is a much stronger base than Cl-, for example, and forms the weakly acidic hypochlorous acid. HOCl Ka equals 3.5 times 10 to the negative 8. Calculate the pH of a 0.1 molar aqueous solution of hypochlorous acid. Okay, that seems like a really complicated problem. So let me translate it for you, and it's basically saying blah, 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 blah. And then this last line here is the only one that matters. So one of the things that they'll do on tests like this or on APs is they'll throw all these wordy questions at you, and you got to learn to cut through what's not important and focus on what's important. And the only thing important in this question is this very last line here with the Ka. They say calculate the pH of 0.1 molar aqueous solution of hypochlorous acid. So let's go ahead. I'm going to do that on a separate piece of paper. I copied effectively that last line on this paper. So let's write the equation. So it's HOCl, so that's an acid. That means it's going to donate a proton. It's aqueous solution. It's going to donate it to water. And what that's going to produce is this OCl ion that they were talking about. It just lost the proton right there, not the electron, so it becomes a negative charge. And like all acids, it produces a hydronium ion. Okay, so that's the chemical reaction. Okay, so what can you do with that right away? You can write a law of mass action for that. You got to remember just one thing, that water is a liquid. Everything else is aqueous. That means water is not part of the law of mass action because it's a pure liquid. So let's go ahead and do that. So Ka, here's the generic formula. It's the products. Everything's a coefficient of 1. That's the nice thing about a lot of most acid-base reactions, in fact, are everything coefficient is 1. It's just 1 to 1 to 1. Everything breaks down. One acid molecule breaks into a conjugate base and a hydronium. 1, 1, 1. All right, so we got that, and it's going to be this on the product side. And on the bottom, the only thing we have is HOCl. Okay? All right. Okay, so we're trying to get a pH from this, and we have one concentration that we're given only, and that's the 0.1 molar of hypochlorous acid. So we're going to make an ice table. I'm going to go ahead and rewrite the reaction. You could have done it from the original reaction up here if you wanted. And it's reversible, so we're going to do that. It's reversible because it's a weak acid. It's not one of the 6 strong acids. That means the hydronium can detach from the HOCl, and then it can reattach itself. It can stay in an equilibrium situation. As complicated as this problem seems, this question, it's going to seem very easy if you do 5 or 6. They all start to look the same. Now I'm going to have an ice table. I'll even put the R there if you like rice. So there's the ice table. Okay? And the first thing, since water has nothing to do with these reactions, you're going to learn to do this quickly too. You just put a line there. It has nothing to do with the it has to do with the reaction, but it has nothing to do with the law of mass action, with the equilibrium equation up here. Okay, so HCl, it gave us an initial concentration of 0.1. Everything here is a coefficient of 1, so we're going to say it's going to go down in concentration because it's a reactant. And since the coefficient is 1, this coefficient is 1. Now we're going to come over here. This starts off, because it doesn't tell us otherwise, it starts off with 0. Again, that's just an assumption you have to get used to in these ice tables. And again, it's 1, 1, 1, 1. Everything's a 1-to-1 ratio. So now this is going to increase because it's a product. And this is going to increase because it's a product. Put that there. And so 0 plus x is going to give you x. 0 plus x is going to give you x. And over here you have 0.1 minus x. So now we have an algebraic expression of our equilibriums, and that's what we're shooting for, among other things. We want to know the concentration of this. Once we know the concentration of this, the hydronium, we can figure out the pH. All right, so we just set this into an algebraic equation. Now we're going to look at something here. We start off with a concentration of 0.1. We have a very, very small Ka value. That means very little change from reactant to product with a number that small. That's not super duper small, but it's pretty small. That means we can make the small x assumption that this x is very small compared to the initial concentration of 0.1. So we'll deal with that when we get here to the equation in just a minute. So what we're going to do is write this. We were given a value of Ka up above. It was 3.5 times 10 to the minus 8. And that's going to equal this times this, and those are represented by the x's right there. So it's x times x, and so these two together are going to give me x squared. X times x, x squared. So I'm just going to go ahead and write it as x squared. And that's over this, what's on the reactant side. So it's 0.1 minus x. All right, so if we assume that x is very, very small, then basically small compared to what? Small compared to our initial concentration, 0.1, we can just take it away, knock it out. So now we have this equals x squared over 0.1. Now it just becomes an algebra problem. I'm going to multiply both sides by 0.1. All right, these cancel on this side, so you're just left with x squared on the right-hand side. And this becomes 0.1 times 3.5 is simply going to be 0.35 times 10 to the negative 8 equals x squared. So you're going to take the square root of this, x squared. So you're going to take the square root of both sides to get x. X is going to equal, I simply take the square root of 0.35 times 10 to the minus 8. So we're going to clear everything, and it's going to be second x squared gives us a square root, 0.35 times 10, and it's caret minus 8 close parenthesis, and that gives you the following: 0.1234 zeros 59. Okay, and then I have a formula for to get to the pH. So what is that? Let's be sure we're clear what that is. If we come back up here, to our ice table, that is the value of x, which is the hydronium ion concentration. That's what we wanted to know. If we know the hydronium ion concentration, we have a formula to figure out pH, which is what the question asked us for. So let's write down that formula. So it's pH equals negative log of the hydronium ion concentration. So now we can plug in the number here, this number. You got to use parentheses, not square brackets. Okay, and go ahead and do this on your calculator. Close the parenthesis and hit equal. In other words, I was just plugging it into this formula. I just applied that, and that gives me the number 4.23. And on the solution sheet, if you look at it, they just round it to 4.2 for the pH. So that's your final answer. That's the pH in this problem. So let's go take a deep breath and go back and figure out what you did. They gave you this kind of acid that you probably never heard of, hypochlorous acid. Okay, and they gave you a Ka value. So of all the things you needed, all they gave you was this number right here, Ka. The other thing they did give you, they gave you one other thing. That's the concentration of it, HOCl. So they only gave you two numbers to work with, this one and this one. So what we do is we take the equation and you create an ice table out of it. You start off with this number. That's the only number that you were actually given. But because they didn't tell you there was anything about the concentration of the products here, you assume that there's 0 at the beginning. Okay? So it's just one of the little tricks of learning how to do these problems. So those are 0. You're going to subtract by some unknown amount of change. What you do know is that the coefficient on that X right there is going to be whatever the coefficient is on these products and reactants. And they're all 1s. And that's usually the case in acid and base problems. That makes it easier to work with. So it's 0.1 minus some amount of this HOCl is going to give us, we're just setting up an algebra equation at this point, is going to give us 0.1 minus X. Over here you have 0 plus X. Again, because the coefficient is 1, it's just plus 1X. And that gives you 1X. Same thing for the hydronium, which is really what we're interested in this problem. So hydronium is 0 plus X is X. So now down here, we set up our law of mass action. We actually wrote the equation up here. So this represents the X right there. This hydronium is the X right there. And this HOCl is the 0.1 minus X. So it's these two, X times X over 0.1 minus X. So there it is. I took the X times X and just combined it into an X squared over 0.1 minus X. We made the small variable assumption that if this is really small compared to 0.1, you can just ignore it. Remember the example from class? 1,000,000 plus 3 equals 1,000,000 plus 1,000,003. That's approximately equal to 1,000,000. So basically you can ignore the 3 because it's so small compared to 1,000,000. Well, this is so small compared to this that basically it's going to end up being 0.1. Just a little bit off from 0.1. Close enough. Okay, so now it's just basic math. It's X squared over 0.1 equals that. You multiply both sides by 0.1. You get 0.35 times 10 to the negative 8. That's what that would give you. And you got the X squared. So now to reduce that down to X, you take the square root of both sides. Okay, just write that and write that. All right, and that ends up giving you this, 0.000059. And that's the concentration of hydronium. That's what X represents, is the concentration of both of these, in fact, but we don't care about the OCl minus. We care about the hydronium here because we want pH. So if we have the H3O value, the hydronium concentration value, then we can get the pH by the pH formula. pH equals negative log of the hydronium concentration. And so it's negative log of 0.000059. And you punch that in your calculator, you get a pH of 4.2. Is that acidic or basic? It's acidic. It's not really a strong acid. It's not really a weak acid either. It would probably be more considered a weak acid. But that is an acid because it's below 7 on the pH scale. So that would make it an acid. Okay, let's move on to another problem. Okay, we're continuing with exercise 12. And this is a challenging problem. This is pretty much this would be a harder AP problem. Okay, and what it is, it's a mixture of two acids. So let's read this. Calculate the pH of a solution that contains 1 molar HCN, hydrocyanic acid, and it gives you a Ka value of 6.2 times 10 to the minus 10. That's a really small number. That means hardly any of this dissociates in water. Very, very small amount. And 5.0 molar of HNO2. That's nitrous acid. That's another weak acid. And that's, I didn't copy that right. That's 4.0 times 10. Let's correct that. And this is on page 13 of your problem set. That's 10 to the minus 4. Okay. So that's the Ka for nitrous acid here. So this is a much bigger number than this. It's 6 orders of magnitude bigger. So it's 1,000,000 times bigger. This is roughly 1,000,000 times bigger than this. So this one is far more likely to dissociate in water, to break apart in water, than the HCN is. Okay, so that's the first thing we notice. And then it wants you to calculate the pH of that solution where you throw both of those, not just one of them, but both of them in. So how do you deal with that when you got 2 different acids in there at the same time? We'll talk about that. Also calculate the concentration of the CN in this solution at equilibrium. So that's the ion that's going to be formed by this weaker, much weaker acid. How much of that is even going to be in the solution at all? Let's talk a little bit about what a Ka is. It's the equilibrium constant of an acid. So let's take a strong acid, HCl. And I'm going to write the abbreviated reaction here. HCl leads to H plus Cl minus. So what happens with a strong acid? 100% of this turns into this. It totally breaks up. So what do you have at the end? You have 0% of this. You have none of it left. It's gone. And all of it is 100% this. So when you write the equilibrium constant, you get this, H plus, Cl minus, over the reactant, which was HCl. Well, what you're effectively saying is that relationship, since we said 100% of it is H plus and Cl minus, it's 100% over 0%. Well, wait a minute. You know from math from a long time ago, you can't have 0 in the denominator of a fraction. What does that mean? That means effectively this Ka is, the way they write it is much, much greater than, that's greater than signs, than 1. It's a super duper big number. Okay, technically this is undefined, or you could say it's approaching infinity, because this number is really, really tiny compared to this number really, really big. So it's a number much greater than 1. In other words, here's the point. Strong acids, and the same could be said for bases, but put this fact away in your mind. Strong acids do not have equilibrium constants, do not have Ka values. Okay? So the point is this. When you look down here and you see that there are measurable Ka values, that means that they're weak acids. They're both weak acids. Okay, so what's going to happen? Let me just give you the punchline of what's going to happen here. This one is much stronger, the HNO2, than the HCN. That means the HNO2 is effectively going to dissociate first. It's going to react first. And then if there's any room left in the solution for more hydronium ions, then the HCN will react. And so what we do is we compute this problem as though HNO2, the stronger of the two, is the only one in solution. When we get an equilibrium concentration of hydronium ions, those H plus ions in the solution, when we know what that is at equilibrium for just this one, assuming this was the only one there, we put that as a beginning product for HCN. We then figure out how much HCN will dissociate, given that there's already a whole lot of H plus ions from this reaction. Again, let me say that again. This one's going to break up. It's the stronger of the two. We're going to end up with a whole bunch of H plus in the solution. Then we're going to do a second computation with HCN, but instead of the initial concentration of H plus being 0 like we've always assumed before, it's going to be whatever we figured it was from this problem here. Okay? So that sounds like enough to keep your brain busy for the next 15 minutes. So let's go ahead and do that. And so what I'm going to do is I'm going to write the equation for HNO2. And again, I like to write it the long way, H2O plus HNO2. You're putting this weak acid into water. It's a reversible reaction because it is a weak acid. It can go in both directions. And that's going to give you the hydronium. In the last problem, I put the hydronium second. It doesn't matter. It doesn't matter. Okay, plus NO2 minus. And that's the conjugate base of HNO2. All right, so there's your chemical reaction. All I did was subtract an H from here. The H from here went over there. Not all of them go over there, just some of them, just some H plus ions to become H3O plus, and there's the H3O plus on the product side, and then there's the nitrous acid without its hydrogen. So that's the conjugate base. Okay, so why don't you just go ahead and you make your ice table right here. ICE. Water is ignored in these reactions. Forget about it. It's a pure liquid. Okay, this, it said we started off, let's go back and read the question, with 5 molar of HNO2. So we're going to put a 5.0 there. Okay, and we're going to subtract X. Because again, the coefficient here is X. Everybody's coefficient is X. And that's going to give us 5 minus X. Over here, we start off with 0. We add X. So down here in the equilibrium, we end up with X. Same thing here. We start off with 0 of this. We add X. And we end up with X down here in the equilibrium. So there we go. There in algebraic form are our equilibrium concentrations of each of these. Now we're going to go ahead, write our law of mass action. And that's going to be okay, so convince yourself that this is the equation for this reaction up here. Okay, let's come over here and just plug things in. So we have X times X, that's X times X. So we're going to call it X squared just like we did in the last problem. And this is 5 minus X. This one is 5 minus X. That's the concentration of the nitrous acid. Again, we're going to make the small variable assumption. And what's that going to equal? That's going to equal, they gave us for the nitrous acid 4 times 10 to the minus 4 for the Ka. Okay, so if X is very, very small compared to 5, we can just take it away. So now you have X squared over 5 equals this. And that's some math you can practically do in your head. You're going to multiply both sides by 5. There. So that's going to become Ka equals 20 times 10 to the minus 4 equals X squared. Here, so okay, 5's cancel out there. 5 times 4 became 20 right there. And then that leaves the X squared on that side of the equation there. I flipped the sides around, doesn't matter. Now you take the square root of both sides. Go ahead, let's do that here on the calculator. So it's second X squared, 20 times 10 caret negative 4 close parenthesis equals, and that gives us 0.0447, let's just call it 0.48. So X equals 0.048. So that is our hydronium ion concentration right there. Okay, it's also the concentration of the NO2 minus, but we don't care about that. We care about this. All right. Okay. Here's the thing. We're not done with this problem. We don't want to know the pH just of this. That would be as though this were the only thing that we were putting in the water, the HNO2. It's not. We're also putting in the HCN. So we're only halfway through this problem. We got to work at a second time now for HCN. So you always do the stronger acid first, figure out what its hydronium concentration is. That X for the hydronium is 0.048. Now we're going to go back and work the same reaction for HCN. So it seems like a really long, complicated problem, but you're really just doing the same thing twice. So let's go ahead and write the reaction for HCN. So HCN plus H2O. Let me just do it in the same order I did it. It's not a big deal. I'm going to put the H2O first. It does not matter. H2O plus HCN will give you, it's reversible, so I give it a double arrow, will give you H3O. Now this is what we're interested in ultimately to find pH, is the hydronium concentration, the H plus concentration, plus CN minus. So it's not really hard to write these reactions. Okay, they're about as easy a reaction as you can write. Okay, we make an ice table out of this. And we go ahead and start filling it in. So we have water is never a part of the equation, so we put that through. Okay, it tells us the molarity of HCN to start with. It's 1 molar. There it is right there in the question, 1 molar. So we're simply going to put a 1 right here. We're going to subtract some amount of those H's that are going to break up from the CN's. That's going to be that concentration. It's going to give us 1 minus X. Okay, now here's where it's different. Normally we've always said that the hydronium at the beginning, just like we did up here, was 0. But it's not 0, is it? What is it? We created some hydronium with that first reaction, that strong acid reaction. There it is right there. That's now the concentration when we start the second reaction. So we're going to put 0.048 as our initial concentration for hydronium. We don't have any CN in the solution, so that is a 0. And now this is going to be plus X, and this is going to be 0.048 plus X, and then X here. All right, so that's the if you want to call it the trick or the point of this, doing this a second time. We figured out the strong acid first, then we used whatever concentration of hydronium it produced, this number, and we put that as our initial hydronium concentration as a product for the second reaction. Why is that significant? Because this is, remember Le Chatelier's principle. If we have more of this product than we had up here above where there was 0, it's going to make the reaction want to go backwards, or to put it another way, it's not going to go forwards quite as much as it would have if we had only put HCN in pure water without an already existing hydronium concentration. So this concentration is going to keep the reaction from wanting to go to the right. It's going to not go to the right as much, that is from reactants to products, as much as it would have. Okay, let's set up our equation. So Ka Okay, and let's plug in our variables now. We don't just have x squared anymore here. We have 0.048 plus x times x over 1 minus x. Okay. So we would really not like to have to multiply those two together. That gives us an x squared and makes it a quadratic. So you know what, we're not going to do that. What we're going to do is use the small variable assumption and say that this is going to go away. And it's a fair assumption in this because this x is so small. When your Ka is 10 to the minus, we haven't written it down yet, it's up at the top, is 10 to the minus 10. That's so tiny that hardly any of this reaction is going forward anyway. even if you didn't have an initial hydronium, hardly any of this reaction goes to the right. So you can assume that this change is very, 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 very small. So let's go ahead and write it down here. So I have 0.48 over times x, so this times this, and the Ka we have is 6.2 times 10 to the minus 10, that's from the original problem. So 6.2 times 10 to the negative 10 equals 0.048 times x over 1 minus x. Okay, 1 minus x. So the algebra is going to be a little messier, but it is just algebra. Okay, so here we go. I'm going to multiply both sides, and I'm going to have to go to another piece of paper here in a second, by 1 minus x. Get on screen here. Okay, so there you go. These two are going to cancel. And now I'm going to shuttle over to another piece of paper here. And I will try to keep all of it on screen at the same time if I can. Give me a second. Okay, so there we go there. So I'm going to treat this like just one big piece of paper. All right, so 1 times this is going to give us this, 6.2 times 10 to the minus 10. And then negative x times this is going to give us minus 6.2 times 10 to the minus 10 x. And that's going to equal 0.048 x. All right, so we have this minus this equals this. So we're going to collect our similar terms on the same side. How do we do that? We add plus 6.2 times 10 to the negative 10 x to both sides. Okay, this goes away, and you end up with 6.2 times 10 to the negative 10 from up here. And over here, you end up with this. 0.048 x plus 6.2 times 10 to the minus 10 x. Okay, here's a math question, not a chemistry question. What's the relationship in terms of size of these two numbers? Look at this. This is 4.8 times 10 to the negative 2. This is 6.2 times 10 to the negative 10. This one is tiny, 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 tiny compared to this one. So again, we can use a small number approximation, a small variable approximation, and just get rid of this. Okay? I mean, 4.8 times 10 to the minus 2 is, I'm pulling this out of my head, I think it's 10 million times bigger than this is. So it's 10 million times bigger, we can ignore this. Okay. But in a multiplication division situation, you can't ignore it. All right, so we're going to divide both sides by 0.048. And that's going to equal, these are going to cancel. The x is still here though, so x is going to equal that. So let's get on our calculator and figure that one out. And then we'll remind ourselves as soon as we do the math here, what does that x represent? So it's 6.2 times 10 caret minus 10 divided by 0.048, and that equals a really, really little number. And what I'm getting is this. I'm getting x equals 1.3 times 10. My calculator's cutting it off here, but I'm getting 1, 2, 3, 4, 5, 6, 7 zeros. So move the decimal. 1, 2, 3, 4, 5, 6, 7, 8. So 1.3 times 10 to the negative 8. Okay. And what does that x represent? Let's go back up above. In our second ice table, this number represents this x. Oops. Yeah, in our ice table, this x would go into here to figure out what the hydronium concentration is. So it's not just simply x. That's the concentration of the Cn minus is this number down here. It is that number for this x. But for this we have to add it to 0.00 to 0.0048. Okay, so what we get for x is 1.3 times 10 to the negative 8. So now that we've worked all the mathematics here, what does that represent? Well, if we come back up to our second ice table, because that's what we're interested in, and we're interested in the equilibrium line here, we can see that x is the concentration of Cn minus. And that's one of the questions they asked us. They said also calculate the concentration of the cyanide ion, Cn minus. So that's it. Now the answer that you'll see on your sheet is 1.4, and that's a rounding issue, okay? But good enough, okay? I'm going to say that's good enough. 1.3 times 10 to the minus 8 is off just by 1/10. It's off by just a tiny bit. That's insignificant, so that's a good answer. Okay, now here's the little bit trickier part. If you want to know the concentration of hydronium, because it's asking us, the initial thing it asked for was the pH. At the end of the entire reaction, that's going to be this hydronium ion concentration here. So what is it? It's 0.048 plus X. So we have to come back down here and say that the H3O plus concentration equals this 0.048 plus, and the X that we just calculated, this. I'm going to sound like a broken record here in a minute. I'm going to say the same thing. It seems like you've heard 100 times. What does this approximately equal? Oops, let me get on screen. What does this approximately equal? So again, what I did was 0.048 plus X. There it is right there, 0.048 plus X. Look at that. What can you tell me about that? Again, for the third time in this problem, this number is really big, 4.8 times 10 to the minus 2, compared to this number. And again, this is not quite as big as it was up above, but it's a million times bigger. Minus 2 versus minus 8, that's a million times bigger, give or take. Okay, so that means this goes away. You don't even have to add it. So your hydronium concentration is approximately 0.048. And you might have said, why did you go to all this work? You already had a 0.048 at the beginning, and now you have it at the end. So what is that telling you? It's telling you that almost all the hydroniums came from the strong acid, the NO2. That almost no more came out from the weaker acid, the HCN. So you end up with approximately the same concentration. Very little of the HCN dissociated. And so therefore you can go ahead and calculate the pH of the entire solution. That might not always be the case, but it generally will be in these problems where you have one weak acid that's much stronger than another one. So we're going to just do our formula. We want to know pH equals negative log of the H3O concentration. This is right off your roadmap, which equals negative log of 0.048. And when you plug that in, you get 3.2. So pH equals 1.32. Their answer, again, it's a rounding issue. It's how I rounded things, but it's still a good answer. Theirs is 1.35. We're going to take that. Close enough, okay? So this seemed like an insanely complicated problem, so let's just again talk about what was the strategy. The strategy is you threw 2 weak acids in, or it doesn't necessarily have to be 2 weak. It could be a strong and a weak, but you had one that was definitely stronger than the other. So you compute the reaction for the strong acid first using the ICE table and the law of mass action, the Ka, the equilibrium equation. Go back to your roadmap sheet and you'll see that these two always work together. The ICE table and this equation are used almost always together to solve problems. When you use one, you use the other generally. Or definitely when you use the ICE table, you use this. Okay, so with that, we figured out the hydronium concentration, which was 0.048 of the stronger of the 2 acids. Now with that as the initial concentration for the next reaction, so that's not a 0 in the second reaction that we're going to compute, the one for the weaker, the much weaker acid, that's going to be our initial concentration of H3O. So we now figure out, we do the same series of steps, and you'll find out these steps are the same all the time. The hardest part for some of you will be the math, but it's basically high school math, integrated math too, at the highest here. So you figure that out, and you come out at the end of the day with the fact that pretty much the H3O concentration, even after you've reacted the weaker acid, is still 0.048. Almost none of the weaker acid dissociated. It pretty much stayed together. Okay, with 10 to the minus 10 equilibrium constant for the weaker acid, that is so tiny that even in pure water that hardly dissociates. When you already started off with a hydronium concentration that's going to keep it from reacting, it's going to react even less. So you ended up at the end of the day with effectively 0.048 as your hydronium, your H+, your H3O+ concentration. So now you take that number and you figure out the pH, and it's 1.32. They have 1.35. Okay, if you practice 3, 4, 5 of these, they're not going to seem that scary, but you got to practice them. Okay, if you just looked at this one, you're going to be going crazy. All right? Okay, I'm going to wrap this video. We're going to be doing these all week, but I'm going to give you a pace on Tuesday. I would like you to try to get through, about 13 by Tuesday over the weekend. We did everything 1 to 10 in class. So I'd like to get through as many more as you can. I'm going to say actually maybe through 15. And I'm doing them all for you, so there's no reason to not get them done. All right, I'm going to stop this video. I'm going to publish it and go on and do a part 5, and that's going to start up with exercise 13.